Here we're going to talk about linear and angular speed. So before we go very far into what linear and angular speed are, how do we calculate speed generally? And speed, and sometimes we call it velocity. Velocity has to do with not only speed, but also the direction of the speed. But so, excuse me, speed for, this isn't a good notation. So let me just say speed is equal to, well, how do we calculate it? We take the distance traveled divided by the time it takes to travel that distance. In other words, if we travel 120 miles in 2 hours, then our average speed was 60 miles per hour, wasn't it? Okay. So here's what we're going to do, though. We're going to consider a particle. So we're going to consider an object. I called it a particle here, but we're going to consider a particle or an object moving at a constant speed along a circular arc of radius r. So the idea is that we're not traveling in a straight line, we're traveling along an arc, a circular arc, where if we were to measure the radius of that arc would make in terms of an entire circle, that would be r, okay? So now what we want to do is decide what the speed of this particle is based on a couple of pieces of information, okay? What's the speed of the particle? Well, now remember the way we calculate, and that's called linear speed, by the way. We're traveling circular, but we want to know what the speed would be if we were traveling in a straight line. And so the idea, once again, is how do we calculate speed? Well, linear speed is the distance traveled. Now, in this case, though, the distance traveled is an arc, and we usually call that by an S, don't we? That's the reason I didn't want to use that a while ago. So the distance traveled is actually the length of the arc. I'll call it arc length divided by the time. Okay? And like I said, a lot of times this is called velocity. So in this case, then, the linear velocity or the linear speed is given by the equation. Okay, it's a kind of scripty looking V. It's not a regular V really. Is equal to arc length, which we define by S, divided by time, which we define by T. So that's the way we come up with linear speed, and there's a formula for it. Now, of course, we can calculate S. Remember, we can calculate S because S is equal to the radius times the angle measured in radians. And so if we were looking at this particular distance that we've traveled, here would be our angle, and r, of course, is this distance, this radius there, and so we would be able to come up with the S value and then divide that by time. Okay. In addition, that if again, theta is the angle that we make when we travel that distance, that arc length, and it's in radian measure, we're going to assume, well, then we can discuss what's called the angular speed of the particle. And the angular speed of the particle is that angle theta divided by time, the angular speed. So it's kind of like saying, of course we measure in radians, but it's kind of like saying, oh, 30 degrees every 1 second. That's how fast it's moving. 30 degrees every 1 second, except we would say it in terms of radian measure. Now, in this case, the angular speed is actually given by what looks like a W, but it's an omega, another Greek letter. And of course, the central angle is theta divided by time, which is t. But remember, the central angle has to be measured in radians. Okay, so it's important to remember this for linear speed. It's important to remember this for angular speed. And there's a relationship between linear speed and angular speed, and it goes this way. That the angular speed, that's a v, let's just call it a v, from above, remember, is arc length divided by time. But we said, as we know, arc length can be calculated by taking the radius and multiplying it with the angle in radian measure. Okay, so now we have r times theta over t. But look, theta over t from above is angular speed. So this is the same thing as saying r and replacing theta over t with angular speed, w there, or omega. So velocity, or a linear speed, pardon me, can be written as the radius times the angular speed. That is a third form that relates the two together. Let's look at a couple of problems, finding linear speed and potentially finding some angular speed as well. Okay, the second hand, as you see, here's an example of a problem we might be dealt with, we might have to deal with. The second hand of a clock is 10.2 centimeters long. Find the linear velocity of the tip. Okay, so how fast is the tip of the second hand traveling as it passes around the clock face? Well, let me draw a little diagram here. Well, here's my clock, and of course I've got an hour hand and a minute hand. The hour hand is the short, thick one, and the minute hand is the long, thick one, and of course the second hand is right here. It's usually smaller or a different color, and that's what's 10.2 centimeters long. And of course the second hand travels around a lot faster than anything else, doesn't it? So now I need to worry about how I'm going to solve this, okay? We need to know the linear speed. So, you know, the linear speed formula says, or linear velocity, I guess is what the same difference. It says that we need to know a distance traveled, which is an arc length, divided by a time. That's what we need to know. Okay, so somehow or another, we've got to come up with a distance traveled and how long it takes to travel there. Now, one thing that we could do here is that we could say, look, let's just imagine we know how long it takes that second hand to travel all the way around. Say all the way around. We know how long it takes that second hand to travel. So, and that's what? 60 seconds, isn't it? Okay? 60 seconds, 1 minute. So we can come up with a time, and we can come up with an arc length that is traveling all the way around. But we have to be a little bit careful about this arc length, because that basically, as that second hand travels around, the tip is, if you will, drawing a circle. And so the radius of that circle is 10.2 centimeters long, isn't it? So in one revolution, which is going to be a 1 minute or 60 seconds, okay, in one revolution, that's going to be 60 seconds, which is really our time amount, isn't it? Then the arc length traveled S is calculated by the radius times the angle measured in radians. Now, in this case, the radius is actually 10.2, isn't it? 10.2 centimeters. And in one revolution is 2 pi, isn't it? 2 pi. So if we've got to measure it in radians, we can say 360 degrees, but we'd have to change it to radians. And so 1 revolution is 2 pi radians. And so we have the arc length then calculated. The arc length itself then, if we approximated that, well, it would be, actually, we don't even have to approximate it. It would be 20.4 pi. 20.4 times pi, 2 times 10.2 centimeters. Okay, so now for the linear speed, and that's what we need, okay, the linear speed being s divided by t, and what we did is we used an s amount that was 60 seconds in elapsing, that 1 full revolution, and that arc length we decided was 20.4 pi, and it took how long? Our time was 60 seconds. And so now we just calculate, and by the way, here we have centimeters and here we have seconds, don't we? And so our units will be, our speed will be in centimeters per second. And so we would just now do a calculation with our calculator and get approximately 1.068 centimeters per second is how fast that's traveling in a linear fashion. Oh, well, that wasn't too bad, was it? Well, let's look at an example on the next page of angular and linear speed, okay? Angular and linear speed. Okay, so we have a tractor-driven lawn roller here that has a 10-inch radius, and as the tractor is pulling it, it's making 1.2 revolutions per second. So there's 2 parts to this. First, find the angular speed of the roller given in radians per second. And secondly, find the speed of the tractor that is pulling the roller. Oops, this is the solution for A. Okay. Now, what did it tell us here? What's it say? That the lawn roller makes 1.2 revolutions per second. So every second it goes 1.2 revolutions. Now remember, to calculate angular speed, we need the angle in radians that it goes through per some unit of time. Okay, now in 1 second, so let's just use seconds here, okay? In 1 second, because that's the information we have, is in 1 second, this makes 1.2 revolutions. Well, what angle is 1.2 revolutions? For every 1 revolution, we have 2 pi radians, don't we? So in this case, in 1 second, the angle that we go through is 1.2 revolutions, or 1.2 times a single revolution is 2 pi radians, okay? So we'll have 1.2 times 2 pi radians that we move through, okay? So in this case, what do we get? We get 2.4 pi radians per 1 second. And we may just leave it in that fashion because it asks for radians per second. So then we can leave it as, and here's what we've got, we could leave it as 2.4 pi radians per second, and that's the exact value. Obviously, we could approximate that, multiply 2.4 and pi together, but that's good enough for what we're doing here. Now let's look at B. Let's look at B, the solution here. Now, the linear speed, remember, and that's what we want to know is the speed of the tractor. But the speed of the tractor is basically the speed that the edge of that, it's actually the linear speed of a spot that would be on that roller. I mean, that's how fast we're going. So the speed of the tractor is same as the linear speed of a particle that is on the edge of that roller. we're transferring it from that circular distance, that circular speed, which has to be equivalent to that linear speed. How fast is it traveling across the ground? So that's all we need to do to find the speed of the tractor, is to come up with linear speed of a particle that is on the roller. And so how is linear speed calculated? Remember, it's S divided by T, where S is arc length. But arc length can be calculated by R times theta, as long as theta is in radians. So we could say, oh, well, it's just a radius times theta times T. Okay. Now, the deal is, though, we're kind of not told anything except what the radius is. And so we're going to go through the same process that we just looked at a moment ago. Why don't we imagine in 1 second? See? Why don't we imagine in 1 second? So we're just worried about what's going on in 1 second. Now, the radius is 10 inches. Okay? And in 1 second, we just saw that what's the angle that we go through? Well, we go through 2.4 pi radians, because in 1 second, we do 1.2 of a revolution, and 1 revolution is 2 pi radians. And so we have 10 inches times 2.4 pi radians. And that really came from above, didn't it? And so when we calculate this, what we're going to see is we're going to have inches over seconds, and that's inches per second. And in this case, of course, what do we get? 24 over 1 inches, 24 pi, my bad, inches per second. But of course, that's just 24 pi, period. And if we approximate that with our calculator, we get 75.4 inches per second. Well, this concludes what I want to talk about for finding both angular and linear speed, and probably linear speed is the one that we use most frequently. So good luck to you on your homework.